This is the Pearson Edexcel AS Further Maths Corp Your 1 paper. So it's just based on this book. For some reason, it's 5 marks and 10 minutes longer than the actual A-level paper. Not really sure why. If you are doing the whole A-level, I would certainly not ignore these papers. I think it's really helpful, and I think there's some good questions in here. Lots of it is just the same as what's in the real A-level, so these are definitely worth practicing on. But anyway, let's get straight into it. So we first got this kind of matrix question here. So let's write out what this is as a matrix, which is this. And apparently we have no unique solution, which means that this matrix must have a determinant of 0. So let's find the determinant of this and set it to 0. So we do k times the determinant of this, which is, or these two multiply to make k minus these two, which actually makes a plus k. So we've got k into k plus k there. And then we've got minus, we always take away this one times the determinant of these four, which is minus 3k plus 16, and then we've got minus 1 times minus 3k minus 16. And again, we want that to be 0 for no unique solution. So we tidy up a bit, we set it to 0, and we find two values of k, which are 2 and minus 8, but we reject minus 8 because it says k as a positive constant, so therefore k is 2. Good, now it says using k as 2, and if we use k as 2, we can just put k as 2 into here, so we do that 3 times. Using that, determine whether the three equations are consistent. So what we're going to aim to do is try and eliminate one of these variables. So I can see clearly if I name these equations 1, 2, and 3, if I just add 1 and 2, z goes away and I get 5x plus 2y equals 1. And then if I use two different equations, for example, if I do two lots of equation 1 and then take away, I think what I probably meant to do here was equation 3, two lots of this, take away this. Yeah, this should be a 3 here, apologies. So that's a very early mistake in the recording. Let's fix it just for future reference. But anyway, if you put a 3 there, so two lots of equation 1 minus equation 3, I believe gets you 20 there, because minus minus, 6 minus minus again is 8, and then this is 6 minus 2 is 4. Divide by 5, and we end up with the same equation here. And now this is overkill, but if you really want to, you can check the third thing, which is these two equations here. So double this one and and I think add this one actually. So double this one and add this one, and I think you end up with this, which divide by minus 2, I guess you get this, and you have the same thing again. So these are consistent because we're getting the same thing every time for x and y. So yeah, we can say same equation, so it's consistent. And then here, I mean, basically, this is a life hack. I've never seen a question on these papers where the answer isn't the planes form a sheaf. So probably just write that down. They do because this is a line solution, right? But probably just write it down, right? That's just what it is every time. It's seemingly so. Probably don't take that advice just in case they ask a question that's ever not that, but it basically is. Okay, so we have z1 equals this, so we could very quickly find the modulus by just doing 2 squared plus 3 squared rooted, which is this, and find the argument by doing tan inverse of 3 over 2, which is this, to four significant figures apparently, which I don't know why that's relevant, but okay. Find z2. Now, okay, there's a few ways to do this, but the easiest way I think is to say that the product of the two complex numbers modded is equal to the mods of the two complex numbers multiplied. So we can say that, oh sorry, I forgot to write this out. So we can say that z1, z2 modded is equal to mod z1, mod z2. But of course we know mod z1 is what r is, so it's root 13, and we know this is 39 root 2. When you divide by that you get this, so we now know the modulus of z2. And we also can find the argument because the argument of z1, z2 is equal to the argument of z1 plus the argument of z2. So the moduluses multiply and the arguments add. We should kind of just know that. Now, of course, we know that's pi over 4. We know the argument of z1 is this number, which I chose to leave exactly like this because it wants it exactly later. So I thought if I just left it like this, my calculator went round. And then if I just put it into modulus argument form like this, so z2 is just, it's r, which is this, and then just put the theta in a couple of times to make this. If you type this into a calculator and close your eyes and pray, your calculator does give you whole numbers, which is good. I was kind of worried that I'd have to do something more intelligent than this, but nope, calculator just was fine with it and gave me these numbers here, so we're good. Excellent. Question number 3, very nice. You probably saw this in lesson time, to be honest. Any maths teacher who teaches volumes of revolution and doesn't prove this result at any point is not a true maths teacher. And I'm going to go on the record and say that. So anyway, we've got a circle here of x squared plus y squared equals r squared, obviously, because the radius is just r. And okay, let's integrate this around the x-axis. That's going to be the integral between r and minus r of y squared dx, times by pi, of course. Y squared is just r squared minus x squared. We can just integrate that, of course, to make this with respect to x, put the r's in. Just be careful when you're putting them in. There's lots of negatives to deal with, but hopefully we get the right answer and we have exactly what they wanted us to show. Good, you should have seen that in class, quite honestly. Next question is a vectors and planes and stuff question. When you're doing planes in this form, all you need to do is take one point that they give you. It doesn't matter which one. I always just choose the first. And then from that point that you're choosing, find the direction vector to get to first this one and then to this one. So to get to this one is 8 across the x's. You need to add 8 to get from there to there. Add 1 to get from there to there. Add 1 to get from there to there. So that would be my first direction next to lambda. So I've taken that point there. I've written it in column because it's just nicer. And then 8, 1, 1 represents how to get from here to here each time. And then here is just from, again, here to here. So add 4 to get from -2 to 2. Add 3 to get from there to there, add 1 to get from there to there, and this will be unacceptable answer. There's lots of different ones, of course, because you could have chosen a different point to start with. Show that according to the model, the lawn is perpendicular. So this is the plane that models the lawn. Show the lawn is perpendicular to this. So all we have to do is take this vector here and dot it with each of the direction vectors that you've got. So do this, dot this, which is of course just 1 times 8 plus 2 times 1 plus -10 times 1, and hope that's 0, which it is, and then dot it with this one and hope that's 0, which it also is. And if two vectors dotted as 0, that means they're perpendicular, which means this is perpendicular to both direction vectors, which means it's perpendicular to the plane. And that's what we have to argue. Hence, find a Cartesian equation of the plane. Now, the reason that these normal vectors or perpendicular vectors are really helpful is because you can use those to write a different form of a plane, which is r dot this, the perpendicular vector, just equals some k. Right, this is the alternate form of a plane you can write down, which will get us to Cartesian form eventually. But of course I need to find out k, and I do that just by putting in any of the points that I know go through the plane. In hindsight, 2, 0, 0 would have been easier than what I did, but it doesn't really matter. This is -2, -6, plus 10, which equals 2. So k must be 2. It would be the same if you put in these other 2 points. Clearly you can see if you put in 2, 0, 0, it's just going to be 2. That would have been easier. But of course k is 2, and now r represents the vector x, y, z. So when you dot x, y, z with this, you get 1x plus 2y minus 10z equals 2, and that's Cartesian form. Good, there are 2 posts in the lawn, so that's the plane there. I think that's just what I wrote down, yeah it is. You've got 2 posts which have the top of the coordinates of each is this and this. Determine a vector equation. So this is nice and straightforward. You just choose one of the points. It doesn't matter which one, similar to up here. And then you plus lambda the direction from one to the other. So it's basically a very similar idea to the vector equation of a plane. So to get from here to here is plus 16, here to here is -4, here to here is +1, and that's where this comes from. And then I've just chosen this point to start with. State a limitation. Of course, you've all seen washing lines in your life. They don't hang straight because of gravity. So sure, just say that. Point R is this, lies on the line. Determine the closest distance to the lawn. Now remember, the vector equation, the lawn was that. Sorry, the vector equation was earlier. The Cartesian equation is that. Now the Cartesian equation is more useful because in your formula book you'll see this formula here, which is how to find the distance from any point, which they've given us here. So this is this, to a plane in Cartesian form, which we wrote down here. Of course, the only difference is I just would write this as -2 equals 0 for that. And we just shove all the numbers in, and we'll find our distance. So that's just me putting all the numbers in. I've forgotten to do the mod here. I think this actually did turn out to be a negative, but then I just ignored it because, of course, that's what you do. And apparently all of this is in meters, so that represents 1.7 meters, which I think is close to 171 centimeters. And then given that the actual result is 1.5, comment on the, evaluate the model. It's 20 centimeters out, which doesn't seem disastrous. I honestly don't really know what you're supposed to write on these questions. When I mark it, I pretty much always just give a mark because I've never seen people, I've never seen any evidence that they wouldn't give a mark for an answer like this. So I think this is just fine. Just say it seems okay. It's only 20 centimeters out. That seems okay. If it was 50 centimeters out, I'd probably say it's not so good, but it's reasonably close, so we'll just say that. Good, so we have this this cuboid here. Its volume is clearly r times r plus 1 times r plus 2, which we could expand out fairly easily to get this. So that's the volume of this. And now we have a bunch of these cuboids here, starting with height 1, then height 2, then height 3. Of course, we could substitute those values into here to find all the separate volumes, but it would be easier just to write it like this. The total volume for all of the cuboids next to each other would just be the sum of this formula for the volume running from r equals 1 up to r equals n. So I'm just going to say that. Of course, when you're doing sums like this, you can break it into this, this, and this, a bit like integration actually, just because it's the same thing, isn't it? You can also bring constants out, just like you can with integration, and then you use the results which are not found in the formula book. No, sorry, they are found in the formula book. I don't know what I'm talking about, because of course I looked them up, because I of course don't know what they are. But the sum of r cubed is this, the sum of r squared is this. Now this is the one that's not found in the book. You need to just know that's n into n plus 1 over 2. These 2's cancel, this 3 cancels a little bit with that, and we end up with this. And now it's really important here that you notice that you've got an n in common between all 3 terms, and you've also got an n plus 1 in common. And you also get that hint because of this over here. So I'm going to bring that out. So that's just what I wrote before. Bring those 2 terms out, leave behind 1 copy of each there. Nothing here except for those 2 bits, and actually just a 1 here. And now it also wants me to take a quarter out, it seems. Let's take a quarter out, which leaves nothing behind here. You have to make this a 2, because 2 times a quarter is a half, and then make this a 4, because 4 times a quarter is 1. And now I've got almost all we need. This is just going to expand out to a quadratic, so I'm quite happy to just expand it out, collect up, because I know I can just factorize quadratics back again, and I'll have exactly what they want me to get. The next part of this question is a complete waste of time. This is the formula for the volume. They're telling you it's equal to this. I thought there was something intelligent to do here, so I times by 4. I actually even expanded out, even though that didn't feel like the right thing to do. Nothing goes away, nothing cancels. You're left with a quartic, which you're literally just supposed to type in your calculator to get an answer for, and I have no idea why on earth they would bother to ask you to do that. Complete waste of time. What a moron question. Anyway, question number 6, we've got this thing here. Now, I'm going to make this a bit bigger, because question 6, as you can see, is very long. Given A is itself self-inverse. So one way you could do this is you could just find A inverse and then compare them and make them equal and so on. It's actually easier just to say that if A is its own self-inverse, then A times A is equal to the identity matrix, because of course that's what inverses do, so cool. And now of course we can just times A by itself a couple of times and compare coefficients. So for example, 2 times 2 is 4, plus A times A minus 4 must be this one. And of course this immediately gives us what A is. If we rearrange a little bit, A is either 1 or 3. And then we can look, maybe, I can't even remember what I looked at. Did I look at this last bit? 2 times A plus A times B must be this 0, because you get top row. So 2 times A plus A times B must be 0. Now it doesn't even matter what A is here. B just must be minus 2 for that to work, because 2A plus minus 2A must be 0. So we have our answers here, and we have possible values for A, so that's good, and just 1 value for B, so that's good as well. Excellent. Now, using the smaller value for A, which is 1, so we shove 1 into there and we get this. Show invariant points if you transform using this. So let's just take a point x, y. If we multiply it by this matrix, an invariant point stays where it is, so that coordinate is still xy. So xy times this matrix is still xy. Now, of course, we can just multiply this out. This gets 2x plus y equals x, and minus 3x minus 2y equals y. But both of those things just rearrange to this line here. So anything along this line here will be invariant under this matrix. Part 2 then, P represents a linear transformation. Triangle, there's a triangle with these coordinates. Now if you just draw this, firstly I worked out the determinant of P because I kind of knew what I was doing, and it's 3P squared minus 2P. Sorry, plus 2P because it's minus 2P, of course. Now if you draw this triangle, this original triangle here, it's 1, 2, 3, 2, which is just across 2 places, 2, 5, which is in the middle, up a couple of places. Now, of course, that's the distance of 2 across, and it's the distance of 3 up from 2 to 5, which means the area of this triangle is just a half times 2 times 3, half times base times height, which is, of course, 3. Now, that triangle gets transformed and then becomes area 15. So the area scale factor is 5. 5 times 3 is 15. But a result you're expected to know is that when you do a transformation matrix like this, the determinant of that matrix represents the area scale factor. So the determinant must be equal to 5. And we can, of course, just solve this, and we get 2 answers for P. It tells us P is a positive constant, so we reject this one, and we get P equals 1 as our answer. And we're done. We're almost done with this question. This is a very long question about matrices. Don't know why they made it so long. V consists of a stretched scale factor 3 parallel to the x-axis with y-axis invariant. So a point like 1, 1 would just stretch outwards and go to the point 3, 1. right? And I can never remember any of these matrices, so that's actually exactly what I do. I pretend that I know what I'm talking about, which I don't. Take the point 1, 1, which I know must go to 3, 1, and just test the matrix out. Now this doesn't work. This goes to 3, 3, so this is an enlargement, kind of a normal enlargement both in both axes. So that doesn't work. What was wrong with it, though, was that this was fine. We got the 3, which is what we wanted. This was wrong. So if I make that a 1, I think this will work. 3 times 1 plus 0 plus 1 is 3, 0 times 1, and then 1 times 1 is 1, and this is where this point should be going under that. So that's the first bit I need. And then the second bit is a stretched scale factor minus 2 parallel to the y-axis. And I think very logically I can just work out now, well, that must be the 1 now, and that must be the minus 2. And now this should go to 1 minus 2, because the x is invariant, and this is scale factor minus 2. So this should go to 1 minus 2, and it does. So I can verify these are the 2 correct matrices. Now, I want to do both of them, so I just need to do this one times this one. Now, it's worth being careful here. You're doing the scale factor 3 stretch first, which means you apply this to xy first, you get whatever that is, which is, I guess, 3xy, and then you apply the second matrix. So actually it looks like the second one comes first when you read left to right, but it doesn't, right? This one comes first, then this one. This actually, and then we multiply these two together to get the matrix Q. It actually doesn't matter that you get that right in this question, because these would, they multiply, I believe anyway, they multiply the same, whichever way order you do it, but just because these two transformations are independent of each other, right? Because, yeah. So this is the answer. You don't have to be perfect there, but that is Q. And then given U, now remember U was to do with the previous bit, and we found that P was 1, remember? So that's actually this vector. So that's the vector, that's the matrix representing U. Given U followed by V is transformation W, which can be represented matrix R, find R. Now this is where we do have to be more careful, because we're doing U followed by V. So U comes first, U is this vector, so it's that times xy, followed by V. V was the one we found before. This is the matrix V, this is the matrix Q representing V, so that matrix goes in front like this. There should be a minus 2, totally should be a minus 2 in front of that. Have I just got this wrong, or have I just not even bothered to check this properly? I believe that what I'll do is I'll say that I've copied this down wrong. And that should be a minus 2. That should be a minus 2. And then, does this even work? Minus 2. That should be a 2 then, I guess. And then that should be a minus 6. Sure, let's go with that for now and pretend and just move on. Anyway. I don't know what happened there. That's probably going to edit it out. Cool. Unless it's right. Unless what I said is right, in which case it won't. Who knows? Only the person watching will know. Anyway, f of z is equal to this thing. Don't know any of the coefficients. We know one of the roots, which means we know a second root, of course. Just write it down. Now, there's a couple of ways to do this. This is kind of an interesting question, because you don't get any information here. You get the information through this whole making a square thing. So you start drawing these two roots, which go there and there. There's clearly a distance of 6 between them, which means if it's a square, then we can just draw a distance of 6 across like this, and say that point is clearly minus 4, minus 3. So that's another root, minus 4, minus 3i. And then, of course, up here at 4, minus 3i. Minus 4 plus 3i. And those are our 4 roots, and this is great because you can do root stuff with this. You can say this is the product of all 4, this is the sum of all the triple products, but it's actually much easier to just write it down like this. Z minus the first root, Z minus second, Z minus third, and so on. And then multiply out these two, which makes this quadratic, multiply out these two, make this quadratic, and then multiply out those two quadratics, and you end up with exactly the kind of thing you want. A is 4, B is 6, C is 4, D is that, and we'll have our answer. Only a couple of questions to go with here. So it's an induction, so just let n equal 1, show that it's true, which it is, good. So then assume that it's true for n equals k, where k is an integer, and then consider n equals k plus 1. So put k plus 1 into here, which gets this. We can simplify this. Now we need to sledgehammer this assumption step, which is that this is divisible by 17, into here. Now what's wrong with this? Well, this is 1 out, and this is 2 out. So let's reduce that out by 1 by this, because we can just add these together to make that. Now this looks like the assumption step, and so does this. This is 9, this is 2, so we get this. And now what I can do is I can say this is not 9 lots of it, but it's 2 lots of it plus another 7 lots of it. Now factorize out the 2 here, and this is divisible by 7 by the assumption step. and this is divisible by 7 because there's a 7 there. So the whole thing is divisible by 7. So what we've shown here is that if the thing is ever true for n equals k, then it's definitely true for n equals k plus 1. You have a case that works when n is 1, so therefore it's true for all values. Just write something like that down and you are done. Question number 9, we have roots here. So we've got 3 roots. Alpha, beta, gamma must equal minus 1 over 3. It's a minus because it's a triple product, so there's an odd number of them, so minus 1 over 3. Alpha, beta plus alpha, gamma plus beta, gamma must equal not a minus, but minus 4 over 3, which ends up being a minus anyway because of the minus 4. Because, of course, these are in pairs, so there's a plus kind of sign in here, but the minus 4 makes it minus anyway. And then, of course, alpha plus beta plus gamma equals 1 over 3, except that is a minus again, because we've got singular roots here, so we put a minus in front. And these are the 3 results we can use. This, of course, is just if you times that by beta gamma, that by alpha beta, you get this, and then put them together. That is, of course, just this number. That, of course, is this number, and you, of course, get 4 in the end as well. Find the cube equation has these roots. Now, there's a bunch of ways you could do this. I thought the most obvious way of doing it was to essentially do what we just did backwards. So if these are the 3 roots, the sum of the roots are just this plus this plus this, which we already worked out is 4. The sum of the product of the roots is this times this times this, which is just 1 over alpha, beta, gamma, which I know is just 1 over minus a third, which is minus 3. And the sum of the pair product of roots, so this times this plus this times this plus this times this, well, I can put these together a little bit, times this by gamma over gamma, this by alpha over alpha, this times beta over beta, put them together, this becomes alpha plus beta plus gamma on the top, which is this, and this, of course, is just this, and we get minus a third over minus a third, which is just 1. And now I think I can just write it in this form, because these things here just represent this, right? The sum of the roots is actually minus a, because, again, we've got independent roots, like we've got singular roots, so that has a minus in front of it. So it's x cubed and then minus 4x squared, because you need to put a minus in front of here, because again they're singular roots. And then this is the one you don't have to change, but it's already this is the one you don't have to change, which is a plus 1, so that's going to be plus 1x, because those are doubles. It's alpha, 1 over alpha times 1 over beta, that's a double root, so it's a plus there. And then, of course, we just need to use this. Now that's a triple, so we change that sign to a plus, and we get plus 3. And I think this will work. Work backwards from here if you're unsure. So think to yourself now, okay, whatever the roots are of this alpha, beta, gamma, the product of the roots is alpha, beta, gamma equals 3 over 1 with a minus in front, which is correct. Product roots is minus 3, and so on. And you can work it out from there. But we'll have our answer. This is the very last question here. Now this here, they've written obviously badly, so we need to fix it for them by putting a bracket into here. This is a circle, center 3, 5, radius 2r. And this is a line starting at the point 2, 0 with that angle coming out of the axis. So it looks a bit like this, I guess. Starting at 2, 0 with some angle here of 3 pi over 4. Now, people are going to be shouting at the screen right now. I promise I'll fix this later. I just couldn't be bothered to edit the slides all the way through. So anyway, yeah, we've got some circle centered at 3, 5. Just going to guess that's here. It's not going to matter, as you're going to tell later. And now this apparently has 2. We need to be on this circle, and we also need to be on the line. So right now there are 2 complex numbers that do that, right? Here and here. And we need to find the range of values for r, which is of course the just when you edit the circle to make it bigger and smaller, that mean that what range of values can we change it to always have 2 roots? Now the thing is, if you make the circle too big, because this line stops here, if you make the circle too big, it passes underneath the line and you only have 1 solution up here. And likewise, if you make this circle too small, you don't reach the line at all, because it's a little bit too small. So there's a range of values of r, the largest of which gets you to touch it here. Right? So this is the largest the circle can be just touching the point here. And we can just do a bit of Pythagoras on this. So we can say across here is 1, up here is 5, so 1 squared plus 5 squared square rooted gives us root 26. Now we can't actually be root 26, because the line doesn't actually start at the point 2, because if you were on 2, there's no angle upwards. So we have to be just less than this. And of course that represents 2r, so 2r has to be less than this. So therefore r is less than root 26 over 2. And that's our upper bound. And what about the lower bound then? Well, this time, this is an incredible picture, right? We have a little circle here that just touches the line. And the way that I thought about this was, okay, let's just do Cartesian coordinate stuff. Let's find the Cartesian equation of this circle, the Cartesian equation of this line, set them each other, and we're just expecting one root, which means discriminant 0. Let's just do all the regular A-level math stuff. This is when I realized that this line is in completely the wrong place, which some people have been shouting at me for the entire time. Angle 3 pi over 4 is, angle pi over 2 is here, right? So 3 pi over 4 is this way. One way you can, by the way, that's the Cartesian equation of the circle, of course, center 3, 5. This squared is 4r squared, just be careful. So the line is over here, and the circle actually needs to look a bit like this to touch it. But like I said, it didn't really matter. You can think this through logically what the gradient of this line is, because like I just said, pi over 2 is straight upwards, pi is straight across, so 3 pi over 4 is logically right in the middle, gradient minus 1. Or you can say gradient is rise over run. But of course, tan of this angle is also rise over run, so therefore tan of the angle is also the gradient, so we can just do tan of this to get minus 1, and that's the gradient of this line. And of course, if the gradient is minus 1, you can do it either way. If this is 2 across, this is 2 up, so the y-intercept is 2 as well, just because it's an isosceles triangle, it's gradient minus 1. And we get this, and we put this into there, and again, we're only looking for one x solution here. Only one. If there are two x solutions, that's 2 roots. We want one x solution here. So we expand out, stuff cancels, which is really nice, and then we can divide by 2. Remember, we only want one x solution here. So how are we going to get that, considering when we square root, we can have either a plus or a minus? Well, the only thing that doesn't square root to 2 things is 0. Of course, this can't be negative, because then we can't square it at all, but if this was 0, x would only have one answer here, because the root of 0 is just 0. So we say this is 0, that gives us this result. We can root this for 3 over root 2, rationalize for this. And that's the exact r value that would touch the line, so anything bigger than that would give us 2 solutions. So we want to be bigger than that, but we want to be less than the original one we found before. Thank you so much for watching, and I will see you next time.